Alright, so in this video we're going to look at one of the applications of calculus, and that is kinematics. So kinematics is the study of the motion of objects. So if we've got, say, a person walking from one side of the room to the other and back, how can we describe their motion or their displacement? How fast are they moving? What's their acceleration? But it's not just people that we can do this with. We can do it right down to really, really tiny objects such as particles and atoms. So the physics still stays the same. So the first thing we're going to talk about is displacement. So displacement, and let's write it up. Let's make sure I spell it right. So displacement is how far an object has moved from the origin. Let's just say you get up out of your chair, you walk to the bin to put something in it, and then you walk back to your chair and sit down again. Your displacement is actually zero for by the time you get back, but because the chair is the origin. But we can actually map out how far away you are from where you've started using physics, and if we knew the equation, from the time that you went to the bin and back and sat back down again. So by the end of it, you haven't moved far at all, because you're still sitting in the same spot as when you got back, unless you decided to move to another chair. So we use, for our displacement, we generally define it as a function of which is s t, and where t is time. Time cannot be negative, so we're going to say that t is always going to be greater than 0. Greater than or equal to, should I say. Because we can have the initial time being 0. Alright. The next one I want to talk about is velocity. And we'll give this the function of v t. Again, where t is just time. So if we were looking at a function f of x, x is in this case time, and f is s or v, depending on which one we're going to use. So what is velocity? Velocity is the rate of change of displacement. So think about that, the rate of change of displacement. So when we've been going through calculus, isn't rate of change of an object just its derivative? Well, it is. So what we can actually say is that velocity is just equal to the derivative of displacement. Now, it's worth noting that velocity is, especially when we're talking in physics, velocity is a vector. So velocity can be negative, it can be positive. We just need to, it depends on where we're looking in terms of where it started and which initial direction it was heading, and defining it. So the negative or positive is really like a vector. So if we look at let's just say we've got a bit of a line here, and we're going to say its position as an object that starts here at position 0. It's going to move down and then back that way. What we're saying is, in this case, when the velocity is greater than 0, when velocity is greater than 0, the object is moving to the right. If it's less than 0, it's moving to the left. Now, obviously, if it's equal to 0, the object's not moving at all. Or at that instantaneous section, it's not moving at all. So you can see over here, if we were to think about this point here, it's not moving to the left or the right. At this point here, its instantaneous velocity is 0. Imagine if this was vertical. You've got a ball in your hand, you throw it up, and you let it hit the ground. So you start off about chest height, throw it up, and then it hits the ground. So the next one we're going to look at is acceleration. And acceleration is just its rate of change of velocity. So again, rate of change, it's the derivative of this. So let's give acceleration the function at is just equal to the derivative of the velocity function, which in turn is equal to the second derivative of our displacement function. I also want to talk about speed, and this is the speed of an object at any instant is the magnitude of the object's velocity. So it's worth noting that we're talking about the magnitude of the object's velocity, not the actual velocity itself. You can't actually have a negative speed, but you can have a negative velocity. So velocity is, I mentioned velocity is a vector, so it can be positive or negative depending on which direction it's heading in. Speed is always going to be positive because it's the magnitude of that vector. Alright, so let's think about this. So if we're going to do some more sine diagram stuff. So let's go here. If we have a sine diagram that says that V and VT and AT are both positive, or negative. So if we look at a sine diagram, let's just take a point, let's just T. If they're both negative or both positive, let's just change this into positives. They're both negative or both positive, then the speed is going to be increasing. If we've got them where it's one is negative and the other is positive, then speed is going to be decreasing. So what we can actually use sine diagrams of all of these for is to look at where an object is located relative to its origin. So let's use the example of getting up and putting some rubbish in the bin, where the origin is the seat that you're sitting in. So we can use sine diagrams to interpret, okay, so you're X distance away, you're travelling at a certain speed, and we can actually see whether your speed is increasing or decreasing based on these sine diagrams. Hopefully that makes a bit of sense. We're going to go through an example now, and we'll look at for a function and a particle. Alright, so in the example that I'm going to go through, we've got our displacement function here. S of t is equal to t cubed minus 6t squared plus 9t minus 1. And it's worth noting that this displacement is in centimetres. So the first thing we're going to do is find expressions for the particle's velocity and acceleration. So remembering that velocity is just equal to the first derivative of the displacement function. So let's go ahead and just write down the first derivative. So, derivative of t to the power of 3 is just 3t squared, minus the derivative of 6t squared, which is just 12t, plus the derivative of 9t, which is 9, and the derivative of minus 1 is just 0. So that is our velocity function, and let's do our acceleration while we're here as well. So remember, acceleration is just the derivative of the velocity function. So here we've got 3t squared, so the derivative of that is just 6t. And we're going to take the derivative of 12t, which is just 12. And derivative of 9 is 0. So we also have to find the sign diagrams of these. So let's have a look. Can this be simplified? Well, we can take out a factor of 3 and we'll get left with t squared minus 4t plus 3. Now this can be factorized, so let's do that. So we're going to have 3 numbers that multiply together to get 3. When they're added together they get minus 4. So that is just going to be minus 3 and minus 1. Alright, so you can see that when the velocity is equal to 0, x, in this case t, is going to be equal to 3 and 1. So for our sign diagram, we're going to have points at 1 and 3. Alright, so let's now go through and work out what the signs are doing. So we'll substitute in a value of, let's just pick 0 because it's nice and easy. So if we put in a value of 0 here, we can see that the velocity at time 0 is going to be positive because this is going to turn into 0, this will be 0, and we're just left with 9, so that's going to be positive. And let's pick 2 and see what that does. So 2 squared is 4, 3 times 4 is 12, take 12 times 2 is 24, so minus 12, plus 9 is going to be minus 3, so in here it's negative. Let's pick 4 this time. So 4 times 4 is 16. 16 times 3 is 48. Minus 12 times 4, which is also 48. Plus 9. So we've got 48, take 48, which is 0. Plus 9 is a positive number. So over here, it's positive. So that's our sign diagram for our velocity function. Let's have a look at, see if we can get one for our acceleration function. Now we can take out a factor of 6 here, and it would become 6 t minus 2. So in this case we're going to have a sign diagram to make all this 0, where t is equal to 2. And we'll have this as a t. Alright, so let's have a look what's happening either side of 2. So let's substitute in 1 and see what's happening. So 6 times 1 is just 6 minus 12, so that is minus 6. So we're going to have negative this side. Let's go 3. 6 times 3 is 18, minus 12 is 6, which is a positive. So there are our sign diagrams. What we're going to do is look at the next bit, which is find the initial conditions. And so initial conditions are when t is equal to 0, and describe the motion at this instant. So what is it doing? What's its displacement, what's its velocity, what's its acceleration at time equals 0. So let's go at t equals 0. Let's have a look what's going on here. So S0, 0 cubed is just 0. So any point where I've got t is just going to be 0. So in this case, our displacement is going to be minus 1 centimeter. What's our velocity at this point? It's going to be 9 centimeters per second. And its acceleration is going to be minus 12 centimeters a second per second. So at time equals 0, all we have to do is look at our 3 equations that we've got, substitute in wherever we've got t for our initial condition, just ignore the values or any term that's got t in it, and look for our constants. So you think about time being equal to 0, it's where x is equal to 0, which is our y-intercept for when we're looking at those. Alright, so that's our initial conditions. What we're going to do now is find the position of the particle when it changes. So when does the particle actually change direction? So we're looking at when does its displacement change. So its displacement is going to change at times where velocity is 0. And we've already worked that out. We already know that when time is equal to 3 seconds or 1 second, velocity is equal to 0. And we know that this is a change in displacement. So what we need to do is, with our displacement formula, substitute in the values of 3 and 1 and see what is it actually doing at this point. So let's do it over here. So we've got S, let's start off with 3, is equal to 3 squared minus 6 times 3 squared, sorry I said squared for cubed, plus 9 times 3, take 1, and it is actually a cubed. So 3 times 3 is 9, times 3 is 27, minus 3 squared is 9, 6 nines are 54, plus 9 times 3 is 27, take 1. Alright, what is this all going to equal to? Well, I'm going to grab out a calculator and punch the numbers and see what I get. 27 minus 54 plus 27 minus 1 is equal to minus 1. Alright, and let's find, so its displacement at this point is minus 1 centimetre. And let's find S1, which is a little easier, because 1 cubed is just 1. Take 1 squared is 1 times 6 is 6. Plus 9 times 1, which is just 1, take 1. So 1 take 6 is minus 5, plus 9 is 4, take 1 is 3. Alright, so what this tells us is that the particle changes directions when it's 3 centimeters to the right of the origin. Remembering, if we're thinking about it, if you have our origin here, let's call it O. If it's to the right, it's positive. If it's to the left, it's negative. If you want to think about it in terms of a graph, then this here would be your y-axis. Along here is x, and everything to the left of the origin is negative, everything to the right is positive. Alright, so the particle is going to change direction when it's 3 centimeters to the right of the origin and when it's 1 centimeter to the left. What we can actually do now, and this is going to be really interesting for me to draw, is draw a motion diagram of the particle. So let's see how well I can draw this. Alright, here is, we'll make our origin in the middle, and we're going to have 1, 2, 3, 4, 5, 6, and these are our centimeters, and 1, 2, 3, 4, 5, 6. So minus 2, minus 4, minus 6 centimeters. Alright, so what we're going to do is look at, we know that our initial condition, our displacement, starts at minus 1. It starts there. When time is equal to 1, our displacement is 3 centimeters to the right. So we know our object has to be up here. Now, it's not to say that it's moved 3 centimeters, its position is 3 centimeters from the origin. In fact, in the first second, it's actually moved 4 centimeters. So let's draw a line in there. Now, at time, when time is equal to 3, it's back at minus 1. So let's draw it up there. And we'll loop around. And we know that it changes direction here, so we know that it must come back here and do something off like that. So that is a very interesting motion diagram, and I should put in here that this is when t is equal to 1, and this one here is when t is equal to 3. Alright, so the next part of this, for what time interval is the particle's speed increasing? So we've got to think about, back to what I said earlier, that the speed of an object, again, its magnitude, and the signs of our velocity and acceleration are the same. So they both have to be positive or both have to be negative for it to be increasing. And if it's opposite, it's decreasing. So let's have a look. So if we look back to our sine diagrams here, we can see that they have the same sign in this kind of region here between 1 and 3. It's negative. Under from less than or equal to 2, it's also negative. So we can say that the speed is increasing. Speed is increasing when t is between 1 and 2. Now, the reason it's between 1 and 2 and not 1 and 3 is because 3, when time is equal to 3 for its acceleration, it's actually a different sign. So for here where it's up to 3 it's negative, over here it's only up to 2 where it's negative. So we're going to write this down as 1 less than or equal to t less than or equal to 2. There's also another point where it's increasing. We see that this sign here and this sign here are the same. Again, it's at 3 here. It starts at 3 here. It starts at 2 here. Back at 2 here, it's negative, which is the same here, but the signs are different. So at here where it's 2, it's negative. Here where it's 2, or let's just say 2.5 to make a real clear distinction. 2.5 here, it's negative. 2.5 here, it's positive. So when it gets to 3, they both are positive. So the speed is increasing for 1 less than or equal to t, less than or equal to 2, and when t is greater than or equal to 3. And the final thing I want to do is find the total distance travelled in the first 3 seconds. So how far has it actually travelled in the first 3 seconds? Well, if we have a look here, it's gone 4 centimetres that way and back 4 centimetres. So it's really just 4 plus 4 is equal to 8 centimetres. If the question asks what's its displacement after 3 seconds, well, its displacement is 0 because it's back where it started. If we think about, so what we're looking here is how far has it travelled in 3 seconds, and that's where one of these motion graphs or motion diagrams can actually come in really handy. So it starts there. After 1 second it's travelled 4 centimetres. Remember, it's starting at -1 to 3 is 4. From 3 back to -1 is also 4. So we've travelled 8 centimetres in the first 3 seconds. Alright, in terms of real life speed, that's pretty slow though. So almost the same as slowly moving a pencil across a page. Alright, hopefully that makes sense. If you've got any questions, come and ask. We're going to look at exercise 3E and go through some of those very shortly. And again, thank you for watching.